Hey class, Mr. Bean here for Honors Physics. Had a special request to go over Lab 44 again, do a redo, talk a little bit about how we find the gravitational constant, which is big G, and also talk a little bit about little g. Now, before I start, I do want you to pause the video and go ahead and do some reading here. Now, this was on one of our study guides, but it might have been a while back since you read it. So go ahead and pause the video and go ahead and take a read this, or it's actually on the lab sheet, attached lab sheet. So make sure you do read this and kind of go over all the information here about the theory behind Newton's universal law of gravitation. All right, so we'll go ahead and go down here to part two here. So again, this is the universal constant, gravitational constant, big G. Go ahead and take some time, pause and read this. Okay, now this is big G. So this is the value that we are wanting to try to find in our experiment today. So we will say it's 6.67 here, 6.67. We're going to use the E notation, e to the minus 11. Okay, so this is the notation we have to use whenever using spreadsheets or online calculators, or especially when we use Quick Tool or we use values from over here. All right, we'll go ahead and let you read this here and go ahead and scroll down some more. And this is the experiment that was performed after Newton passed away. So actually 150 years after Newton's discovery, some guy named Cavendish and some other people came up with an experiment in which they were able to calculate what big G was. So go ahead and kind of read this here and kind of see what we've got going on and take a look at the apparatus that they used. Okay. And a little side note here. So people are wondering about little g as compared to big G. Well, let's go ahead and take a look and see what we got going on here. All right, so so what we have here is, let's go ahead and kind of draw a circle here, pretend like this is the Earth here, okay? And we'll assume it's a circle, and this is R, the radius here. And we have, let's say, some person standing on here like so, and draw a little head here. Okay, and this guy here, his mass will be little m, and this is the Earth, let's say, and he will have a big M for the mass, big M. Okay, so what's happening is that from the center here to here is R, and there's a force of attraction between this mass and the mass of the Earth here. So what happens is that we'll go ahead and kind of write this out here. And so this is going to be F is equal to, this is going to be big G here, okay? This is going to be the mass of the Earth here times this little m right here, which is mass of the person, divided by the radius of the Earth squared. Okay, and this should be little m here, little m here. Yeah, this little m. Okay, little m here. All right, so what we got here is that we know from experiments that we've done in class that little g here on the Earth has the value of 9.81 meters per second squared. So the question is, where does this value come from? Well, if we take a look here, let me go ahead and use a green pin here. I'm going to go ahead and kind of highlight this part right here. So if we just take this part right here and kind of move it off the side here, what happens is that this together is what we call little g. Okay. Now, sometimes this is referred to as the gravitational field strength or gravitational field. Okay, so it's made up of big G here. Here will be the mass of the Earth here divided by the radius of the Earth squared. Okay, so this is little g. Now, if we plug in the value for big G, put in the mass of the Earth and the radius of Earth squared, what happens is that we get the value of 9.80 meters per second squared. Now up here I wrote down 9.81, but you could say it's 9.80. Okay. All right. So this is little g. It measures the gravitational field strength. So what happens then is that we can usually write this as F is equal to, this will be g, and this will be the little m here. And so what happens is that this is the weight. So when we have F is equal to G times M, this is how you calculate someone's weight. Okay, weight, right here, weight. All right, so this is little g. Okay, this is little g here. Now in one of the labs, so this is little g here. All right, so we just now something I do want to add is, let's say we have the Earth here again. And let's say that there's a mountaintop here. Let's see, there's like a mountaintop here, and someone is standing on this mountaintop here. Okay. All right. So what happens now is that this here is R right here. And I'm going to go ahead and use a pink red here to show altitude. So there is altitude. Okay. And we'll call that A for altitude. So now what happens is that if you are on a mountaintop, or further you are away from the center of the Earth, the gravitational field, or the force acceleration due to gravity, weakens. And let's take a look and see why that happens. So this here is big G here. Okay, the mass of the Earth does not change. It's still big M, but this time here, the distance from the center of the Earth is now increased. So we have not only the radius of the Earth, but we also have the altitude as well to add to it. And we'll go ahead and square that. So now what happens is that if this number here gets bigger, this number here gets smaller. Okay. All right. Now let's go ahead and go to the virtual lab here. Okay. Okay, so objective is to find the value of big G experimentally using this equation right here. Okay. Method one is to hold M1 and R constant while we vary M2. Okay. All right. So for our purpose of our experiment here, let's take a look and see what we got going on here. So let's go ahead and first of all, I'm going to kind of slide this guy over here, and I don't like the sound here. I'm going to kind of put him over here. So first of all, let's set the radius. Okay. So we'll go here and let's set the radius. Let's say, let's just go 5 meters. There we go. So the radius is 5 meters. Okay. So we're going to set the radius here as 5 meters. So make sure we put an M here to indicate meters. And M1, let's go ahead and just make M1 100 kilograms. So we'll make M1 100 kilograms. Okay, so this is set. Okay, so we can only manipulate one variable at a time. So 100 kilograms. All right, so let's go ahead and let's start with M2 being also, let's say it's 50. So so M2 is 50. So we'll go ahead and put here 50 like so. Make sure we draw it. Gosh, hold on. I can't write this very good here. Bad cursor. So we'll go, this is 50 here. Okay. Now what's F? So up here is force M1 by M2, and this is force M2 by M1. So look closely, they have the same magnitude but opposite direction. So it's 1.28 E negative 8. So we'll go over here, 1.28 here, right? And make sure that's an 8. E, make sure you write E here, negative 8. All right, negative 8. All right, so now let's go ahead and increase this to maybe 100. Let's go 100 here. All right, make this like 100. So this is now 100. Okay, there's 100. And make sure we draw 100. Now what's the force? It looks like it's 2.57 here, and E negative 8. So there's E minus 8. Okay. All right. So now let's go ahead and increase this. Let's say, let's go 200. Or 180 is fine. Go ahead and do 180 here. We'll make this 180 here, like so. There's 180. And the force is now 4.62. So we'll go ahead and put down here 4.62 E minus 8, like so. All right, there we go. All right, and let's go ahead and maybe increase this to, let's say 260. Yeah, So this is now 260, and well, that's hold on. Make sure that that's at 5 centimeters there. That wasn't at 5. So we'll probably have some error here. So 6.94. So 6.94, like so. E minus 8. So here's E minus 8. Okay, now these values might be off a little bit because I wasn't exactly at 5 meters here. So which is good. It'll give us some a little bit of an error. All right, and let's just do one more just to be sure. Let's go with 340. So these can be any random numbers, but we'll just go ahead and just choose these numbers here. So there's 340, and make sure that the force is, this is going to be, hold on, the force is going to be 9. Man, hold on. Cannot draw very good here. Okay, the force is going to be 9.08. Okay, 9.08 E minus 8. Now, if you look closely here, as we increase the mass here, we see the gravitational force getting stronger. All right, so now let's go ahead and go to Quick Tool over here. This is a quick graph tool here, and make sure we fill this out up here. Now, what did we actually change? So here we changed M2, which is in kilograms, like so, okay? And what we changed was dependent variable is going to be the force, which is in newtons, like so. All right, so we're here, and let me make this a little bit smaller so we can kind of see what's going on here. All right, there we go. All right, so over here, so let's go ahead and plug in the values for M2. We have your 50, right? So there's 50, we hit tab 50, then 1.28 E minus 8, okay? Hit tab. Next one is 100, tab 2.57 E minus 8, okay? And 3 would be 180, good. And this will be 4.62 E minus 8, okay? And this will be 260, 6.94 E minus 8, okay? And finally we have here 340, and this will be 9.08 E minus 8. All right, so there we go. And if you look over here at this graph here, looks like it's pretty linear. It looks like it's a straight line. So let's go ahead and do curve fit. And we'll go ahead and choose linear. Okay, there we go. All right, so now let's see what this, so extract, now the technique to find big G is called extracting the answer from the slope, okay? So let's take a look and see what the slope is here. And let me take a quick look at this, see what we got here. Okay, so, oh, it makes the graph a little bit bigger. All right, so we can see the equation here is y, right, is equal to, here we have 2. Let's say 7, right? 2.7 E here. They have minus 10. They got minus 10 here. All right, and we don't have to worry about this other part over here. All right, so let's go ahead and let's see what we got going here. And let's go ahead and make it back smaller again. All right, so there's the slope here, okay? And this should be x here, right? X here. Okay, now let's take a look at our equation here, and let's see what we got. So here we have, here's F here, right? F is equal to big G. That's what we want to find. There's big G. This will be M1, right? And this will be M2 here, right? And this whole thing here is over R squared, right? Now, I'm going to use green here, okay? Now this part right here is constant, right? Big G, M1 and R did not change, right? They were constant, as is G here. Now take a look closely here. Isn't this just like Y is equal to MX, right? Okay, these things correspond here, okay? So the slope, right? The slope, okay, the slope is equal to what's inside the bracket here. Is equal to big G, so here's M1, all this divided by R squared, Okay, so all you have to do now is find, this is the slope here, right? There's the slope. Plug the slope in here, uh, and M1 is right here. Here's R. Go ahead and plug that in and solve for G. Big G should equal what? Okay. Go ahead and solve that for big G. All right, so I hit pause. So when I solved for big G, I got big G was equal to 6.6. Hold on. I did not get that. Go ahead and erase this here. I got 6.75 e to the minus 11. So this was our experimental G. Now the actual G, okay, so I'll go ahead and put down G here and star for the, and put an asterisk here. The actual G value is 6.67, right? E to the minus 11. So we should be able to do a percent error here and see what the difference is. All right, so that's for you to complete here. All right, so now let's go ahead and take a look at method number 2. So method 2 says to hold M1 and M2 constant while changing R. Okay, so let's go back over here now. Okay, so let's go ahead and hold M1 and M2 constant. All right, so here is M1 and here is M2. So let's go ahead and M1 is what, 340? So let's go ahead and put down here 340. Let's just go ahead and use those values there. Okay, 340, and it's going to be kilograms, right? Okay, and M2 is 100 kilograms. So there's 100, and here is kilograms. All right, there we go. All right, so now what's our starting R value? Here we have 5, right? So let's go ahead and just put down here 5 meters. And what is the force? And it looks like it's going to be 9.08, right? 9.08. And we'll make sure we close that up here. E to the minus 8. Minus 8. All right. So now let's make it 6 meters apart. They're 6 meters apart. So we'll say 6 meters apart. And now the force is 6.3 here, 6.3. And this is going to be E to the minus 8. Okay, looks like it's getting smaller, right? All right, so now let's go ahead and go to 7. There's 7 meters. Okay, so we'll say 7 meters apart now. They're 7 meters apart, and this is now 4.63 E minus 8, like so. There we go. Okay, and now let's go to 8. Okay, so now it's 8. Okay, so we now have 8 meters apart. Okay, so this is now 3.55. This should be 55 e to the minus 8. Okay, and let's go ahead and just go to 10. I'm just curious. Let's just go to 10 here. So there's 10. Well, we can't quite go to 10, so let's just go to 9. All right, so there's 9. So 9 meters apart here. And this is going to be 2.8 E minus 8, like so. All right, so there we go. All right, so we can see here as we increase the distance here, the force of attraction decreases. And we're not sure if this is exponential yet, or if it's linear, or what we got going on. All right, so let's go ahead and go to quick graph here. And let's just go ahead and just graph what we have here, first of all. Okay, so we have here, this is going to be R, right? So this is going to be R, and it's going to be in meters, like so. Okay, and this is going to be force. Okay, so the R values are going to be 5, right? And this is going to be 6. This is going to be 7. This is going to be 8, and this is going to be 9. Okay, now the force is going to put in the force here, 9.08 E minus 8 for that one. Okay, and we'll go here. This is 6.3 e minus 8. Okay, the next one here is looks like 4.63 e minus 8. Okay, and next one is 3.95. So we'll say 3.95 e minus 8. And then finally, last one here, we have 2.8 e minus 8. Okay, now let's say, okay, now this, let's see, make sure we have everything in here. And okay, hold on. Oh no, this should be 3 here. Made a mistake. There's 3. Okay, and let's see. We have, let's see, do we have everything here? Oh, 3.95 e minus 8. Okay, so obviously it's not linear. Okay, so let's go ahead and get rid of the graph here. And let's see, how do I get rid of this graph here? Okay, so let's try like a what's it? Inverse square. Okay, all right. So it looks like it's kind of an inverse square. Okay, there's an inverse square relationship here. Inverse square. Okay, and all right. So it's inverse square relationship. It looks like this here. Okay, now how do we extract the answer from the slope? Okay, good question. All right. So what we need to do here is let's look at the equation again. So here is f, right? Here's f here. And here we have big G again. Okay, we want to try to extract the answer from the slope. Okay, but I don't see a slope here. So let's see what we can do. Okay, so this is going to be m1 here. This is going to be m2, right? And I'm going to go ahead and write it like this, 1 over r squared. Okay, I'm just going to rewrite it a little bit here. Okay, like so. Now, G, m1, and m2 were all constant, right? These were all constant. So this is going to be y is equal to, here's mx. Okay, so here the slope, okay, the slope, if we get a slope here, the slope will equal big G m1 m2. Okay, that's what G will be. Okay, however, when we make our plot here, we have to do 1 over r squared. Okay, so this here is just looks like this is just r. Okay, but we need 1 over r squared. Okay, so what that means is that, so here's 5, right? So it's going to be 1 over 5 squared. Okay, gosh dang it, 1 over 5 squared, right? Which is 1 over 25. And that should equal 1 divided by 25. Hold on. 1 divided by 25 equals about 0.4. So this would be 0.04. Okay. So what I need to do over here now is I need to go ahead and make this, rewrite this. Let's make this 1 divided by r caret 1 over r squared. Okay. So the first value here is going to be 0.04. Okay. 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 0.04. 0.04. Okay, good. All right. Now, 1 over 6 squared is 1 divided by 36, okay, which is 0.027. Okay, so 0.027. Okay, 1 over 49. Okay, so 1 divided by 49 is equal to 0.02. Okay, and this is 1 divided by 64 equals 0.015. Okay, and then finally 1 divided by 81 equals 0.012, like so. All right, there we go. Now this kind of, well, yeah, kind of looks like a linear equation here. It looks kind of straight, so let's go and do linear. And yeah, it kind of matches up here. Okay, so now what we got here is, so let's get the slope. So let's go ahead and go here. Okay, so the slope is right here. Okay, so the slope, right? So we'll go ahead and write down here, slope, right? The slope here, and it's going right in here. Slope equals, looks like 0. Okay, so it's going to be 1, 2, 3, 4. Okay, let's do scientific notation. 1, 2, 3, 4, 5, 6. Okay, 6. Okay. So we'll say 2.17 e to the minus, let's see, one more time here. Okay, so 1, 2, 3, 4, 5, 6. E to the minus 6. There's our slope. Okay, there's our slope. All right, now we said then the slope has to equal this right here, has to equal, so the slope has to equal big G. Okay, there's big G. Here is M1, and here is M2. All right, so plugging in these values for M1 and M2, you go ahead and calculate big G. All right, so what I got for big G here is I got a big G value of, looks like 6.38, okay, e to the minus 11, okay, and remember the accepted value is 6.67 e to the minus 11. So go ahead and do a percent error calculation and see how close we were. All right, that will conclude redo of Lab 44. So go ahead and use the attached document to get this completed, and see you in class.